Today's speaker is Giacomo Nannicini from University of Southern California. It's a great pleasure to have him. And he's going to tell us about quantum optimization and state-of-the-art in this area. So Giacomo, please take it away.
Thank you. Thanks for inviting me. Feel free to ask questions at any point in time. By the way, I will not be looking at the chat. So if you want to ask questions, unmute yourself and say something, because otherwise I would not see. I wasn't, exactly sure what the audience is going to be, but I'm going to assume essentially that everybody shares at least the language of applied mathematics, and so this presentation is really targeted for applied mathematicians of various types. So maybe if I can, okay, good. Sorry, the window had lost focus. So the talk is about quantum computing, and where there is interest in quantum computing from many points of view. From my point of view, the interest is due to the fact that it is a different computational paradigm compared to classical computers. And by the way, I use classical to say something that is not quantum. So in principle, operations can be slower or faster in classical or quantum computation. It really depends on what you're trying to do. But we know for a fact that there are certain things that can be done faster on a quantum computer compared to a classical computer. And the two things that spurred interest in research and algorithms are groundbreaking work in the 90s done by Shor and Grover. Shor's algorithm for integer factorization lets you factor integers in polynomial time, and it's not known to be something you can do in polynomial time with a classical computer. And with Grover's algorithm, you can search over n elements in an unstructured manner in square root of n time, giving you a quadratic advantage. So these are two very well-known pieces of work, but of course there's many more algorithms, and you can look at that link if you want to see a list, which is mostly compiled from a theoretical computer science perspective. Now, my background is in operations research and in optimization, and I like to think about efficient algorithms for problems. And so I care about quantum computing because it gives me a different way to look for efficient algorithms. There might be things that we don't know how to do classically, and we might be able to do them with a quantum computer, or there are some things that maybe we already know how to do them classically, but the quantum computer might give us different trade-offs, and that might work better for some problems. It's also true that the technology for quantum computers, for quantum computing hardware, is improving very rapidly. And so in some sense, even though right now the hardware is far from being perfect, I think it's reasonable to expect that it will be of good quality soon. And so in some sense, this will give us new toys to play with if you, like me, are a computational mathematician and like to have, think about algorithms and run algorithms and try to do something hopefully useful. So my goal is going to be to talk about optimization. And so in particular, I would like to discuss at least what I know in terms of the utility of fault-tolerant quantum computers to solve classically defined optimization problems. I will specify what I mean in just a couple of slides, but I do want to emphasize the fact that most of what we discussed today is going to be assuming the existence of a fault-tolerant quantum computer that actually does not exist in reality. So I mentioned a few things that could also work on non-fault tolerant computers, but mostly I will assume that essentially that we have hardware that can perform things in the ideal way that matches the abstract model of computation for quantum computers, and we know that we cannot do that yet. Okay, so as I mentioned, the focus is going to be on optimization, and I'll talk about combinatorial and continuous optimization. But first, let me just give an overview of what I mean by, being provably useful at solving classically defined optimization problems. So an optimization problem is a mathematical problem of the form that you can see here on this slide. And mathematical optimization tries to solve this problem. So you want to minimize or maximize some objective function subject to a bunch of constraints. And you want your vector of decision variables to belong to some set and also satisfy all the constraints, of course. And the set of points that satisfies all the constraints of the problem is called the feasible set. This problem is used for optimal decision making in many areas of business and engineering and science. And so being able to solve this class of problems in a way that is practically efficient has real and very tangible business impact. There are many industries where this type of problems is solved routinely, and the impact of this problem can range in the hundreds of millions of dollars, being able to solve it well. Even if you don't care about, about engineering in general, and you're more into the whatever is fancy these days, you should also keep in mind that every time you train a neural network, you're really solving an optimization problem. So being able to solve these problems well is extremely important in many areas of engineering and business and science in general. Now, when we talk about an optimization problem, generally, as I mentioned, we want to be able to solve the optimization problem, so find the solution that minimizes and maximizes the objective function. It is important at this point to make a distinction regarding whether the data for the problem is classically defined or quantumly defined, and similarly, whether the algorithm is classical or quantum. So it's conceivable, and there are optimization problems for which the data that defines the problem is quantum in some sense. And by that, I mean the fact that, for example, the data might describe some, might give a description of some quantum mechanical system, or some of the data of the problem might come from the simulation of a quantum mechanical system. So there are optimization problems of that type. And these are the problems that on this slide I'm calling physics problem for lack of a better word, but typically they are related to some sort of physical meaning of a quantum mechanical system. And you may want to solve those optimization problems using either a classical algorithm or a quantum algorithm. If the data of the problem is classically defined, and really here you should think about there is, the data is stored on a hard drive that exists on your laptop. That's a classically defined optimization problem. Well, assuming that the data is not described in some quantum mechanical system. And so if you try to solve that optimization problem with a classical algorithm, you have classical optimization, traditional optimization. And that is what is typically the focus of a significant part of industrial engineering department, for example. But you can also try to solve classically defined optimization problem using a quantum computer. And that's going to be the focus of this talk. And I'm going to argue now already, and you'll see the reasons later why, that this is probably the hardest setting, because there are many difficulties that we face when we try to use a quantum computer to solve a classical optimization problem, and we don't have any of the natural advantages that come when trying to apply a quantum algorithm to a problem that describes a quantum mechanical system. If the data for the problem is in some sense quantum, then that data is going to be in some sense difficult to represent or handle classically. And so it's conceivable that the quantum computer has an advantage. But if your problem is classically defined, then you don't have that advantage. And so our focus here is going to be trying to solve classically defined optimization problem using a quantum computer. And then I also mentioned that I'm interested in provably useful optimization, and that's not very well defined, but I'll tell you at least at a general level what I mean. So optimization is a discipline that is rooted in practice. The reason that it is so pervasive and many people study it in certain departments at least is the fact that it has real business impact. And optimization as a discipline is defined as something that it's really at the prototypical applied mathematics. You want to solve problems numerically and use the solution of those problems to help business decisions or engineering problems. So my ultimate goal here is to develop algorithms that can solve real-world problems. On the non-quantum side, I've done a lot of work on practical solution schemes. However, when we talk about quantum algorithms, it's very difficult to assess the numerical performance at this point in time because the hardware is imperfect. And so for most of this talk, I will discuss theory. There will be some references and some discussion of what things can be done numerically, but most of what I discuss here cannot be executed on existing quantum hardware. And so we're limited to discussing the theory of these algorithms. All right. Any questions so far?
Okay. Can I ask something which
Yeah, of
was
course.
Related to the previous slide on the classical versus quantum type of problem? So
yes,
on the right-hand corner, do you mean something like quantum simulation of quantum systems on the right-hand upper corner? Is that the type of problems that you have here?
Yeah, for example. So suppose you're trying to solve an optimization problem in which you want to choose some parameters that will lead to a good outcome after a quantum mechanical system evolves in time. It's possible that for an algorithm like that, because you're trying to optimize something that depends on the time evolution of a quantum mechanical system. That's something that I don't know how to do classically well, I mean, at least in theory, and I might be able to do that much better with a quantum computer. And so that might give me a natural advantage in parts of what defines the optimization problem.
Okay, so the data here is basically representing the problem description. Is that?
That could be, yeah. So the data here is the description of the problem. Generally, that's what I assume here, and this data might be in the form of it might describe a quantum mechanical system, in which case maybe the full description of the system lives in the exponentially large Hilbert space, and that might be difficult to handle. Or even if the data is, yeah, I mean, I guess that's probably I should stop here. Next thing I was going to say didn't make a lot of sense. Yeah. So if you think you're describing a quantum mechanical system, then there is a classical description of the data, but what you're really trying to optimize lives in something which is more quantum than classical.
Okay, makes sense. Okay, thank you.
Of course. Okay, so I'm going to start with discussion with combinatorial optimization. And so combinatorial optimization is the type of optimization that you have when the set of possible decisions is discrete. And so generally, the feasible set would be a subset of the integers. And there are many famous combinatorial optimization problems, such as traveling salesman problem or the bin packing problem, when you want to choose how many containers you need if you want to fit a certain number of items. This is what Amazon solves, for example, when you pack your delivery trucks. Maximum independence set, and so on and so forth. There's many famous combinatorial optimization problem, and many of the interesting combinatorial optimization problems are NP-hard. That means that there is no efficient algorithm that is known or expected to exist. It's also widely believed that quantum computers cannot solve NP-hard problems in polynomial time. So every time I say efficient solution, I really mean polynomial time here. And so generally, for the exact quantum speedup. And that's because those combinatorial optimization problems normally will not have an efficient algorithm, and we don't expect quantum algorithms to be able to solve them exponentially faster than a classical computer. I also want to mention the fact that generally, when discussing combinatorial optimization using quantum computer, there is a natural and strong connection to a class of problems that is usually abbreviated QBO. These are quadratic unconstrained binary optimization problem. And the reason comes down to the fact that it's very easy to translate a QUBO into a Hamiltonian. So the Hamiltonian is an operator that encodes the total energy of a quantum mechanical system. Once you have a formulation of a problem as a QUBO, classical optimization problem formulated as a QUBO, it's very easy to construct a Hamiltonian such that the minimizing the energy of the Hamiltonian corresponds to minimizing the objective function of the QUBO problem. However, QUBOs are also NP-hard. This has been known for a long time. And if you put this together with what I just mentioned, we don't expect to be able to solve QUBOs with quantum computers in polynomial time. Now, as usual, with all the discussions about theoretical computer science, when I say we don't expect, it means we know nobody has a proof. If you were able to prove this, you would be extremely famous. But this is what most people working in the field believe is true, but we just don't have the tools to prove it. So yes, it's easy to translate QUBOs into Hamiltonian, but we don't expect a quantum advantage, at least a provable quantum advantage, using quantum algorithms to solve QUBOs. A quantum advantage that is more than a polynomial. So there could be a polynomial speedup, but we don't expect more than that. Now, since, putting together what I just mentioned, very large theoretical speedups are essentially impossible for combinatorial optimization. And I mean, large theoretical quantum speedups are essentially impossible. And so usually people working in the field of combinatorial optimization would say, well, if you cannot prove me that you're going to do better, then can you show me that you're doing better in practice? Which means we're interested in the practical performance of quantum algorithms to solve combinatorial optimization problems. But one should also keep in mind that for many combinatorial optimization problems, classical solution methodologies are extremely well-tuned and will be very, very hard to beat. As an example, if you think about the traveling salesman problem, a notorious combinatorial optimization problem, which is believed to be a hard problem, but in practice, we have very efficient methods to solve it. Already 20 years ago, there is this solver that you can Google and actually use this solver if you want. Already 20 years ago, the Concord TSP solver could provably solve a difficult instance of the traveling salesman problem with about 86,000 nodes. This instance comes from some sort of circuit design problem. And so you can see on this slide a picture of the solution. And so even if you have non-trivial instances of traveling salesman problem with millions of nodes, you can routinely solve them to near optimality in a reasonable time. Now think about the current state of quantum technology, hardware in particular. We don't even have any hope of implementing an algorithm for a problem which is a fraction of the size of these problems here. And so all I'm saying is that there is essentially no way that I see a quantum computer ever beating a classical computer to solve traveling salesman problem, likely in my lifetime. There's so many technological obstacles that would need to be overcome. Now, maybe I will live very long, and then maybe things will shift more quickly than I think, but it seems difficult. Of course, for not all combinatorial optimization problems are as well solved as traveling salesmen from a classical perspective. There still are combinatorial optimization problems that are difficult for classical computers. And for those, then there could be hope for practical quantum speedups. When it comes to existing approaches to solve combinatorial optimization problems using quantum computers, usually they fall into one of these two categories. The first category is quantum heuristics. Here, heuristics means an algorithm that doesn't certify that it found the optimal solution. So there are quantum heuristics that are based on the adiabatic theorem. And for this class of heuristics, existing work focuses on showing that you can get a good solution faster than you could get it on a classical computer. And there are encouraging results in this direction, although I also want to mention that this type of quantum practical quantum advantage, so being fast at finding a good solution, historically has been fragile. And what I mean by that is the fact that it has happened before, and it might happen again, that there are works that show good results in finding near optimal solution using a quantum computer for a certain class of problems compared to classical algorithms. But after some time, the classical algorithms for that class of problem get fine-tuned and improved, and then the classical computers are able to match the performance or often beat the performance of the quantum algorithm. So there has been a lot of back and forth, and that's what I mean when I say historically fragile. There are also heuristics that are really tailored for the quantum circuit model. And these are usually based on defining some parameterized circuit that essentially defines some infinite subset of the quantum states. And then one searches for the best quantum state only inside that subset by essentially optimizing over the parameters of the quantum circuit. This class of algorithms has the main drawback of being difficult to analyze theoretically. So there are some cases that can be analyzed. In particular, the quantum approximate optimization algorithm for very specific cases can be studied, and the performance of the algorithm can be characterized quite accurately. But for most other cases, we don't know how to characterize the performance from a theoretical point of view. And in particular, I do want to mention something because this is fairly common approach in many papers that I read, and I think it's a dangerous approach. So that's why I want to highlight it. So let me start with some quick facts. So if you have a quantum state, the quantum state directly yields a probability distribution over 0-1 strings, over vertices of the hypercube, and if you have a cubo problem, it's easy to estimate the expected objective function value of the distribution associated with a given quantum state. I don't want to go into details, but these things are easy to show. Now, a common approach to construct a quantum heuristic for quantum computers based on the circuit model is the following. You define a parameterization of the subset of the quantum states, in particular by defining a parameterized quantum circuit. And then you use a classical nonlinear optimization algorithm to optimize the parameters of the quantum circuit with the objective function of having a good expected objective function value. Remember, the quantum state gives you a probability distribution of the vertices of the hypercube. So this can be done. It's easy to do. But what I want to emphasize is the fact that unless we have very good intuition on how to choose the parameterization of this set of quantum states, or how to optimize the parameters, this is unlikely to work because the optimization problem that you solve with the nonlinear optimization solver is highly non-convex, and it's very likely to get stuck in bad areas of the search space. As an example for why this could be a bad idea, there's an analogy that I like to use in this case. If you think about trying to solve a 0-1 optimization problem, purely classically, nothing quantum here, you could formulate a 0-1 optimization problem as a nonlinear optimization problem by adding constraint that for each variable, let's say xj, you want xj times 1 minus xj to be equal to 0. The only points that satisfy xj times 1 minus xj equal to 0 are the points where xj is equal to 0 or to 1. So you have a valid nonlinear optimization formulation for a combinatorial optimization problem. The issue is the fact that this nonlinear optimization formulation is horribly non-convex, and there is no hope to get a good solution for this problem in practice. Any solution algorithm you try to use is going to run into a lot of issues and not give you a good solution. And so the same thing can very well happen here. And in particular, I think this approach is a reasonable approach when you can get some analytical intuition in the form of the parameterization of the set of quantum states. So in the form of the quantum circuit, or you can get good intuition on what is a good algorithm to optimize the parameters. But in the other cases, it's very dangerous territory because you're defining a nonlinear optimization problem that is as hard to solve as the original combinatorial optimization problem, and for which we don't really have good algorithms. So this is something that one should be careful about. And so those are some challenges in terms of combinatorial optimization, but what are the opportunities? There are many. In fact, in some cases, it's possible to show rigorous results that lead to quantum speedups for combinatorial optimization. So some of the examples that I know that I find notable are Ambani's and others' works on quantum speedups for some exponential time dynamic programs. The speedup is only polynomial, so the best classical algorithm runs in exponential time. The quantum algorithm also runs in exponential time, but the base, the base of the exponent is smaller. And then recently there has been some work by Jordan and others that they showing a better approximation ratio than any known classical algorithm for a highly structured problem, for which I have to be honest, I don't know any practical application. But for that specific structure of the problem, they show that the quantum algorithm in polynomial time gives you a guaranteed approximation ratio better than the best known classical algorithm. This is not a separation because we don't know, there could exist better classical algorithms. So it's possible that there are classical algorithms that do better than the quantum algorithm, but we don't know them at the moment. And these types of results are very impactful. They usually need to develop new techniques that have a long-lasting effect in terms of the development of future quantum algorithms. There's also, in my opinion, a lot of room for effective heuristics. I feel that we're only scratching the surface of what is the right toolbox to develop quantum heuristics for combinatorial optimization problems. I'm going to mention that if you want to look for combinatorial optimization problems for which there is some hope of quantum advantage, as I was mentioning earlier, in my opinion, you should not look at problems that are already well solved classically. You need to look at problems where classical technology is not very effective. And so for those problems, there could be an opportunity to do much better using different approaches. And if you're interested in those problems, then one suggestion that I have is that you have a look at this quantum optimization benchmarking library, which is part of a joint work with many people. And this gives a benchmark set of combinatorial optimization problems that are difficult already at small size. You can look at the paper or look at that link for the Git repository. The repository includes detailed guidelines on how to submit solutions and results with either classical or quantum solvers or any other technology that you want, and also provides a lot of scripts to help check generation of instances, feasibility of the solutions, and things like that. I'm not going to go into the details, but I do want to mention something here. I am showing here one of the figures from that paper. In that paper, we define, we collect, actually, we don't define, we collect 10 different types of combinatorial optimization problems. Their names are listed here. It doesn't really matter what these mean at the moment. You'll have to look at the details to see what they are. But I want to mention a few important points. The first is that these problems, many of these problems have direct connection to practical applications. An example here, one of these problems here is Steiner tree. This is Steiner tree packing problem. If you can solve Steiner tree packing problems effectively, you can solve routing problems in circuit design effectively, and that has tremendous impact. There are lots of industries that will be extremely interested in this type of solution algorithm. And the other interesting things about here we have many problems that have different characteristics in terms of what the objective function looks like, what their density looks like, what the constraints look like. But the other important thing is that most of these problems are difficult already at very small size. As an example, what I mean by small size, in this plot here, you have on the x-axis the number of variables. And this inset picture shows you in cyan, so light blue, the instances that we could solve to optimality, and in pink, the instances that we could not solve to optimality. And so these points here match the points in the larger picture. You can see that already around 100 variables, there are problems that we don't know how to solve to optimality with a classical computer. 100 variables, maybe a couple hundred variables, is not that large. There is hope that we can implement quantum algorithms for problems of that size relatively soon. And so for those problems, we think that, that those are good starting points for an investigation of quantum optimization algorithms for combinatorial optimization. Okay. So takeaway here is, if you're interested in difficult combinatorial optimization problems for which classical technology is not good enough, I suggest you have a look at these references, that you will find many problems that satisfy that property. Any questions so far before I move on to continuous optimization? Okay.
I have a question. So the density on the graph, how should I interpret the density here?
Yeah, so this density, I should have mentioned, this density is number of, I need to give a little bit of context. So these problems are defined in a sort of abstract way. You could use different models for each of these problems. The density refers to what we think is a natural formulation for these problems as an optimization problem. And the density refers to how many non-zero elements there are in a constrained matrix compared to the total number of decision variables. And by the way, some of the constraints for these problems are quadratic, but so all of these problems can be formulated using either linear or quadratic constraints. And so both for linear and quadratic constraints, there is a natural formulation using matrices, and the density refers to how many non-zero elements there are in those matrices. And this is going to impact directly, but the correlation is not one-to-one, how dense the formulation would be if you formulate the problem as a quadratic unconstrained binary optimization problem. So if you try to formulate the corresponding Hamiltonian with just, let's say, double Z terms, the density would relate to that, but the correspondence is not one-to-one because of the translation, which could change the density.
Mm-hmm. Okay.
Generally, sparser problems are easier to solve for classical technology. There's just less data, and a lot of the solution approaches exploit sparsity of the problem representation. It's not always the case, but generally sparse problems tend to be easier. Although, as you can see here, already around the 100 variable mark, we have some relatively sparse problems like these guys here that are also very difficult.
Okay, thank you.
Yeah. Okay. So now I want to talk for a bit about continuous optimization. And so in continuous optimization, the set of possible decisions is not discrete. Typically, you're looking for some points that lie somewhere in Rn. And there are many famous problems in continuous optimization. For example, training machine learning models is a continuous optimization problem, but also engineering design, so structural design, these sort of things, they usually give you continuous optimization problems, extremely impactful in practice. And there is a growing body of research on quantum algorithms for continuous optimization, which has achieved some form of quantum speedup. But these quantum speedups usually require many assumptions that are unlikely to be verified in practice. And so just as before, I'm going to mention the challenges first, and then later I will mention opportunities. So here are some of the challenges that we face in developing quantum algorithms for continuous optimization. A big challenge is the fact that many of the quantum algorithms have to assume that some crucial numerical parameters characterizing the problem instance scale well with problem size. Examples of these parameters are, for example, condition numbers of certain matrices, or size of the solution, or even just the precision of the solution by which you guarantee an optimality gap or feasibility tolerances. And the issue is the fact that in practice and in theory, numerical parameters of interesting problems usually are not constant. They scale with the problem size. And many classical algorithms that are used in practice have running time that is guaranteed to be polylogarithmic in these numerical parameters. Examples. One of the numerical parameters that sometimes shows up in the running time of algorithms is the size of the solution. So how many bits do I need to describe the solution of the problem? Most classical algorithms that are used in practice scale polylogarithmically in the the size of the solution, not the number of bits. But this is extremely important if you're trying to develop algorithms for certain classes of problem. There is a whole class of quantum algorithms for semi-definite optimization that scale, polynomially in the size of the solution. This is problematic because the size of the solution of a semi-definite optimization problem could be very large. In fact, it could be doubly exponential in the description of the problem instance, and this has been known since the 60s. There's also a whole class of algorithms that use quantum linear system algorithms to solve certain crucial parts of let's say, a main optimization block. And those algorithms generally depend linearly on the condition number of the corresponding linear system. This becomes problematic for certain types of optimization algorithms, in particular interior point methods, because this condition number is known to grow very large. It can be shown theoretically to grow large over the course of the iteration. So it will slow down your quantum algorithm. And also, when it comes to dependence on the precision of the solution in terms of optimality or feasibility, generally, 1 over epsilon could be okay. Once you start getting to an algorithm that scales like 1 over epsilon to the 4th, practically, even if your epsilon is 10 to the minus 2, which is usually not enough in practice, then the performance of your algorithm is not going to be great. And so one has to be very careful about making assumptions on how these numerical parameters scale. Another challenge that we face is the fact that to be efficient, many quantum algorithms assume efficient data access in superposition. So the quantum algorithm wants to take advantage of the principle of superposition, and so it wants to be able to query elements of the problem data, let's say coefficients in the objective function or coefficients in some matrix in coherent quantum superposition. So for what problems do we have a way of efficiently querying the data of the problem in quantum superposition? That happens if you have a small quantum circuit that describes the data. And so that's equivalent to say that you should be able, if your problem is classically defined, you should be able to write, some small number of lines of Python code that describes the data of your problem. You want to query some element of a matrix, the Python code should be able to tell you the value of the element of that matrix. And I want to emphasize, the Python code should be just a few lines. The size of the number of lines cannot grow with the size of the problem. That prevents you from looking up the data of the problem in a lookup table. If you have a lookup table, you have to scan the elements of the lookup table, and all the data of the lookup table needs to be embedded in the Python code. But you cannot do that if you want this efficient data representation. So what's an example of a problem that has an efficient representation of the data? If you look at the assignment problem, which is this linear optimization problem here in the bottom left, look at it constraint matrix. The constraint matrix of this problem is very structured. It looks something like what I'm showing here. It's, this only ones and zeros, and the positions of the ones and zero are very easy to tell once you tell me the size of the problem. I know exactly the structure of the matrix. If you tell me the size of the problem, you tell me I and j, I can tell you if the corresponding matrix element is 1 or 0. I just need to do a couple of ifs. And so for this problem, I can write 3 lines of Python code that fully describe the elements of the matrix. This problem has efficient representation. But most problems that are interesting in industrial setting don't have this efficient representation. And in that case, that will slow down your quantum algorithm, because every time you want to query an element of the data of the problem, you need to essentially scan the entire table that describes all the elements of the problem. So what can you do if a problem does not admit an efficient representation of its data? you can make stronger assumption. And in particular, you can assume that you have a form of storage called quantum RAM that lets you access problem data in quantum superposition. I want to emphasize that this quantum RAM model is a stronger computational model than the standard models for quantum computation. Normally, for quantum computers, you think either of the circuit model or the adiabatic model, which are perfectly equivalent. These two models don't let you implement quantum RAM by themselves, but you can think of a stronger model in which you have circuit model or adiabatic model, but in addition, you have this form of quantum storage. So what does this quantum storage do? It's very easy to describe. Think of classical RAM. Classical RAM lets you access data essentially in constant time. Quantum RAM does the same thing. It lets you access data in constant time, but also in superposition. You cannot implement quantum RAM efficiently in the standard circuit model. If you want to implement the operation that quantum RAM does, and you want to have access to a RAM that describes, let's say, M pieces of data, if you want to implement the corresponding operation with a circuit, you would require a number of gates that is roughly linear in M. But with quantum RAM, you want to be able to do this operation in essentially constant time. Maybe polylogarithmic time in M is okay. However, even though this is a stronger model of computation, theoretically, we don't know, or at least I don't know, and I haven't found in the literature any obstacle to the existence of QRAM. So in fact, most people that I talk to, and I ask this to many people, believe that in theory, quantum RAM is possible. Essentially, the argument is that if I can construct classical RAM, I can also construct quantum RAM. I just need to use quantum gates. However, most experimentalists believe that quantum RAM is going to be almost impossible to construct. There are a number of engineering obstacles to the realization of quantum RAM, and so I don't expect it to be available anytime soon, probably in my lifetime. So fault-tolerant quantum computers might be far in the future, but maybe not too far. Quantum RAM, if possible, is likely very, very far in the future. On the other hand, if you assume quantum RAM, and this is a fairly standard assumption in certain branches of the literature, then you can access data of your problem in essentially constant time and in superposition. So this eliminates, I'm going to go back one slide, this eliminates the problem that I mentioned here. If you have quantum RAM, usually you have efficient data description. But you get further away from implementation. And so what are some of, these are a lot of challenges, but there are also opportunities, and I want to collect here some of the things that give me hope for optimization of quantum computers. Most of these things apply to continuous optimization, but some of these things also apply to combinatorial optimization. And in this short description of certain key quantum subroutines that I feel are promising, I'm giving indicative running times, and so a lot of assumptions apply to be able to obtain this sort of running times, okay? So these are sort of best case scenarios. There are many, many, many assumptions before you can get to this point. So, one should use them with care. But so some of the things that give me hope are, well, to start with, amplitude amplification, which lets you do unstructured search and minimum finding with a quadratic advantage if you're optimizing over a set of n elements that is unstructured. And this building block is crucial for the polynomial speedup for exponential time dynamic programs that I mentioned earlier, where you can show a quantum advantage compared to the best known classical algorithm. Another building block that gives me a lot of hope is Gibbs sampling. Gibbs sampling, you can think of it as sampling from a Gibbs distribution, which is a distribution defined in this way here. But more generally, I think of Gibbs sampling and constructing a trace normalized matrix exponential. So somebody gives you a matrix H and you want to construct this exp of H normalized by its trace. And so classically, if you want to compute this matrix exponential given H, you need to do a lot of matrix multiplication. And so the running time will be, and if the matrix is n by n, the running time will be n to the 2 point something. But on a quantum computer, you can construct a mixed state that corresponds to this Gibbs Gibbs distribution here in time that is only square root of n in certain cases, only in certain cases. And so this is a considerable speed up, and it's used pervasively in quantum algorithms for semi-definite optimization. Of course, the killer application for quantum computers is likely Hamiltonian simulation, and that's the simulation of a differential equation of this form here, where this H is a given matrix called Hamiltonian. Simulation of this type of matrix classically requires time that is exponential in the number of qubits in the worst case, but quantumly you can do it in polynomial time in the number of qubits. And this approach is used to simulate gradient flows and also to escape saddle points in optimization. There's also a solution of linear systems. As I mentioned, if you have a linear system AX equal B, where A is described as a matrix over a certain number of qubits, classical solution requires times exponential in the number of qubits, but quantumly it's polynomial in the number of qubits. This is crucial for quantum interior point methods, but I want to emphasize many, many conditions apply. This is really not an easy type of speed up to obtain. You know, you cannot just substitute your classical solver with a quantum solver and get a speed up. That just does not work. A lot of work is needed there.
Hi, how is this matrix A defined? What do you mean by it depends on the qubits?
Right, so I think in terms of the size, I'm really just thinking about it in terms of the size. If your matrix is, let's say, n by n, I can define it as an operator over log n qubits. And so I have a quantum algorithm that solves, that computes a quantum state describing the solution in time that is proportional to log n, but classically I would take time something like, you know, n to n cube, likely, if you're using LU factorization. But I really want to emphasize there are a lot of conditions for this. It's not a plug and play type of replacement, because first you need to describe the matrix appropriately for the quantum computer, and second, the solution for this problem is going to be encoded in a quantum state, and you cannot get a description of the quantum state. So if you're interested in the full solution vector, then it's going to be difficult to get a speed up from this. In some cases you can do something, but it's really not straightforward. I hope that answers. Yeah, so this is really referring to matrix size.
Okay, thank you.
Yeah. You have exponential advantage in the size, but you have exponential losses in many other things. That's, I guess that's a way to summarize it. Okay, and the last thing I'll mention is gradient computation. So if you have a function, if you have access to an implementation of a function, let's say it's a piece of computer code, and you want to compute its gradient not analytically, numerically, given the implementation of the function, classically, you could do it by doing finite differences, which would take a number of evaluations of the function that is at least linear in the dimension. But with a quantum computer, sometimes you can even do this in constant time, so independent of the dimension. However, this constant time algorithm has many conditions, so it doesn't apply in general. Still, you can get quantum speedups even for some nonlinear functions, certain types of polynomial functions in particular. And this is used in quantum algorithms for convex optimizations in a certain structured manner. And so these are some of the things that give me hope. And I want to give an example of some work that I've recently done with a bunch of co-authors where we use some of these building blocks to try to do something for optimization. And in particular, we're looking at linear optimization problems, so a problem of this form here. It's well known in the classical world that you can solve a linear optimization problem with a path-following algorithm by solving the sequence of better problems with some parameter mu that starts at some value, let's say 1, and then progressively reduced to 0. This type of path-following algorithm is implemented in virtually every existing solver for linear optimization problem. It's very efficient in theory and in practice. And so one thing that we developed is a quantum algorithm that does something similar and also follows essentially the same path as the classical algorithm, but with some differences that I'm going to mention in a second. And this is mostly the work of Brandon, who is a student that I co-advised at Lehigh University, and Jachi, who was a student at Maryland. Other co-authors are Xiaodi Wu and Tamash Terlaki. And so with this idea, we define a quantum algorithm that simulates the trajectory that leads from an initial solution to the optimal solution with a running time that we can bound as essentially square root of the dimension of the problem times the number of non-zeros of the constraint matrix, which is very good. Unfortunately, we still have a couple of numerical parameters that are pretty bad and we could not get rid of. And these parameters are the size of the optimal solution and the optimality tolerance. I don't want to go into many of the details, but I want to give you the main intuition of how we do this. And so here's the sketch of the idea. So classically, we can define a path that starts from a point. So here I have a linear optimization problem. The light blue region is my feasible region. Classically, we can define a path from an interior point, this z of 1, that goes all the way to the optimal solution, this point here at the bottom. And this path is parameterized by some parameter mu that starts at 1 and goes to 0 over time. This is an analytical definition of a path. And classically, you have algorithms that try to approximate this path and follow it to the optimal solution. What we do in the quantum world is that instead, we define a Schrödinger equation such that the trajectory of the solution of the Schrödinger equation follows this path. And so what we do is that we start with a quantum state that is that defines essentially a distribution centered on this point z of 1. This distribution, you can think of it as a Gaussian distribution centered on the path, and it's represented by these spheres here. And then as we simulate the Schrödinger equation over time, the center of the distribution follows the path, and the distribution gets narrower and narrower. And then after a certain amount of time, what we show is that now your quantum state defines a distribution over points that is centered and very close to the path. And so if you take a sample from the quantum state by performing a measurement with very high probability, you will observe a point that is very close to the optimal solution. This is what we use to show the running time bound. This is a sort of picture of the general idea. I also have some very small scale numerical simulation that we did for a toy problem that only has 2 constraints and 1 decision variable. The reason is the fact that we were limited to very small problems at the moment is the fact that I'm going back one slide. So to initialize this simulation, I need to know a point that is exactly on the central path. The reason is the fact that we're going to use an adiabatic theorem argument to show that we can follow the Schrödinger equation all the way to the solution at the end. So I need to analytically know what is the point located on this path. Generally, it's difficult to know a point located on this path unless I take my original optimization problem and I embed it into a larger dimensional problem. There are ways to embed the problem into a larger dimensional problem that guarantee that you know a point on the central path analytically. And so we start with this problem that has only 2 constraints and 1 variable, but then in fact we embed it into a 5-dimensional problem for which we guarantee that we know a point on the central path. And then that 5-dimensional problem is the one that we actually simulate. And so what I'm showing you here in this picture is a simulation projected down on the first 2 variables. And you can see here on the pictures that we start with some distribution of points centered on a point on the central path. The path is depicted by this white dashed line in all these pictures. And over time, we decrease the parameter mu that I showed you earlier in the definition of these better problems. And over time, the quantum state moves along the central path towards the optimal solution, which is this point in the at the bottom right corner of the dashed line. And the distribution also gets narrower and narrower. And really the idea here is the simulation of the Schrödinger equation. So simulation of the Schrödinger equation is the problem that quantum computers were built for, and it can be defined in the following way. Somebody gives you some time-dependent Hamiltonian operator, which is just a Hermitian matrix, and some initial state. Think of it as some column vector, and you want to simulate this differential equation for a certain amount of time. And what we do is that we design a Hamiltonian that has a kinetic energy term, which is the standard Laplacian operator, and a potential energy term. The potential energy term is designed to tell you the distance from the central path. And these two terms, the kinetic energy and the potential energy term, are weighted by some scalar functions of time, h of t and mu of t. We analytically define these functions h of t and mu of t in such a way that we can guarantee that the simulation of the Schrödinger equation performed for a certain amount of time leads you to a point that in the end is a minimizer of the potential energy for mu of t very close to 0. And we show that this is also a solution to the optimization problem. And to do this, we didn't come up with this idea fully by ourselves. In fact, we borrow a lot of ideas from the work that Jiaqi Liang, which is one of the co-authors, and Xiaodi Wu did on simulating gradient descent algorithms with a similar idea. And we modify that idea so that it can provably find solution to linear optimization problems. Okay, so what are the challenges? Well, the main challenge is the fact that this algorithm to simulate the Schrödinger equation is not something that can be implemented. Unfortunately, to do the simulation, at least in theory, we rely on an existing piece of work on the simulation of the Schrödinger equation that uses the full toolkit of fault-tolerant quantum computation. And that cannot be implemented on existing computers. But if you're interested in what you can do on existing computers, look at Xiaodi Wu's work. He has a lot of videos and papers on this idea. And not for linear optimization problems, but for other types of problems, they also have working implementations. And unfortunately, as I mentioned earlier, the running time bounded GIF still scales polynomially 1 over epsilon and the size of the solution, and this is not good. And I don't know how to eliminate this yet. If it can be eliminated, this I don't know. But the opportunities, I think, are enticing because what I showed, this algorithm does not require quantum RAM, and the running time that it gives, at least in terms of the solution size, is actually great. So if you could improve its performance in terms of the other parameters, that would be amazing. Okay, so it's time to wrap up. So summary of the discussion. So for combinatorial optimization, when it comes to quantum computers, in my opinion, it's still unclear whether we're going to be able to get quantum advantage. There are many things that point to the potential of quantum advantage, but the theory does not give clear answers. In fact, it's difficult to show quantum advantage in theory for combinatorial optimization. And in practice, there has been a lot of back and forth. So I think there are many opportunities, but at the moment, there has been no definitive proof that this is useful. For continuous optimization, I would put it closer to high potential that there will, at some point, be actual quantum speedups for continuous optimization. And this is based on all the subroutines that I described to you, where it seems that one should be able to build something that exploits the benefits of quantum computers for continuous optimization. I'm going to stop here. The very last remark is that if you're interested in this area, I have an upcoming book on this topic that is about, at the moment, it's about 210 pages. You can find a preliminary version of the book on the archive. The version of the archive is slightly outdated, but I'm finishing a revision, and I plan to put the final version online in less than a month. And so if you're interested in teaching these topics also to people that don't know quantum mechanics, the book is entirely written for applied mathematicians. There are no physics here. And so if you are interested in that and you end up using it, please send me comments. I'm very glad to take feedback on anything that you see and try to make improvements. And that's it. Thank you. I'm very happy to take questions.
Thank you, Giacomo. It was a very interesting talk. Any questions for Giacomo? Okay, so maybe I can so if you go just maybe I'll go maybe one more slide back. No, just the one before. The book you mentioned, this is your lecture notes, right? Is it
Yeah.
okay. So what okay, maybe I'll ask it later on after the technical questions. I
Yeah.
have a question about the book. Okay. So any technical questions? Okay, so I'll ask a question, which is the path that you showed. I think that was very interesting. If you can go back to
Yeah.
the path that goes to the optimal point, the
Yeah.
vertex feasible region. So so something that is not clear to me. So this blue region is the solution. It is attached to the linear system, and
Yeah.
then you mentioned somehow this path is going to describe a trajectory. Is it something like the path? Does the path live in the quantum states, space of quantum states, whereas the polytope itself is, you know, attached to the linear system? Or so am I thinking it in a wrong way, or are they like, are you embedding this feasible region into?
So you can define this, I'm gonna back to the problem definition here. You can define this purely classically. Somebody gives you a linear optimization problem, you have this polytope, and you write down the optimality conditions for the linear optimization problem. The optimality conditions will have some complementarity constraints that are non-linear. Based on those non-linear complementarity constraints, essentially by checking how much you violate those complementarity constraints, you can define a path analytically. You can, get analytical description of this path that goes from some point interior to your feasible region and leads all the way to the optimal solution, where the optimal solution is defined when you satisfy your initial conditions and also the complementarity conditions for optimality. So this can be done purely classically in terms of defining the path, and it is exploited classically. Now, the question is, you cannot hope to solve the optimality conditions when the complementarity conditions are satisfied in just one step. Classically, this is done in many steps, essentially trying to satisfy the complementarity conditions more and more, and that leads to classical interior point algorithms that approximately follow this path. They sort of zigzag around this path by approximately trying to satisfy the complementarity conditions. What we do here instead is that we define a quantum state that is centered on this path, and then the Schrödinger equation is defined in such a way that the potential energy measures the distance from the path, from that curve. And with an adiabatic argument, we show that if you start in a point that is a minimizer of the potential energy, and you change the parameters slowly enough, then over time, you still stay in a minimizer of the potential energy, which means you stay on the path. And so then the issues show, of course, how slow you need to change the parameters to ensure that you stay on the path. And so really then the quantum state is going to be this distribution of points that is centered on the path. And that's the minimizer of the potential energy.
So is the central path like the expectation value, like the
Yeah. Oh, actually, okay, sorry. Let me think about this for a second. Yeah, so the mean would be on the central path.
Okay.
The mean will be on the central path, and the variance gets smaller. So that's another crucial point, because otherwise, in the end, when you perform a measurement, you might get points that are far from the central path if the variance was very large, but we show that the variance gets smaller. And that's because of the way we control, there are some functions of time here, this mu and h of t. We need to control those precisely to ensure that eventually the variance gets small.
Okay, so the path itself that lives in the feasible region, right?
Yeah.
But is parameterizing some quantum states in your...
Right, so that's how we follow the central. So let's see how to express this clearly. Yeah, so analytical definition of the path is purely classical. It's possible to do, but it's still difficult to compute points on the path. So it can be done, but it requires a lot of time. So you can define, a trajectory that would follow the path, but computing that trajectory is still going to take time. What we do is that we use the quantum computer to follow that trajectory. And one difference compared to classical algorithms is that because we want to follow that trajectory with a quantum algorithm, instead of only considering one point, the simulation is performed at a quantum state, which is then going to define potentially a superposition of points. So in some your quantum states describe a probability distribution over points that might be inside or outside the feasible region, but in fact, for the way we construct it, we show that it's a superposition of points, all of which are around the central path. And then the advancing time in the simulation will make this cloud of points move closer to the optimal solution because of the potential energy. I mean, the trick here is the potential energy is really what we want to minimize, and we reduce, in fact, we would like to minimize the potential energy where mu of t is 0, and then we start with a mu of t that is around 1, and then over time we decrease it, and we use an adiabatic argument to show that you stay in the minimizer of this Hamiltonian.
Okay, I think I have a better understanding, but did you say the distribution is, so the quantum state defines a distribution on this polytope?
It does, yeah.
That's how I should think of it. But then is it correct to say that the points of the polytope kind of corresponds to outcomes of your measurements or something if you're performing on the quantum system?
So if you were to perform a measurement earlier, you would get some point in space, but you don't have. So the quantum state is a superposition of points that could be anywhere in space, in principle. The algorithm ensures that these points are concentrated around the central path. So think of each basis state is a point somewhere in space. So we discretize the space with a grid, and then each basis state corresponds to some point on this grid, which could be inside or outside the polytope that we don't know yet. The algorithm guarantees that your quantum state is going to be a superposition of basis states that are inside the polytope and centered around this curve.
So is it kind of just, okay, I have a wave function whose components are essentially the points of the ambient space of the polytope, and then the algorithm just more or less guarantees that on expectation, I have these points when I do a measurement, they fall inside of this feasible region.
That is correct. Not only inside the feasible region, but around this blue curve. And I want to emphasize that we borrowed a lot of knowledge from classical interior point optimization. This idea of the central path, the neighborhood of the central path, how far can you be from the central path and things like that. These are all things that are known, that have been known for maybe 40 years in classical optimization. There is a lot of classical optimization technology in this.
Okay. Okay. So that was quite interesting. This picture, I definitely want to understand it better. So any other questions for Giacomo? Maybe there is something on chat. No. Okay. Well then, let's thank Giacomo for this talk. Well, thank you very much.
Thank you.